What do you say I could do? Like alt or something plus. No, that's not it. Control plus. There's some way to get it to do what you want to do, but I can't remember. He said I should be able to remember from Wednesday. All right, so I guess people are going to watch this after, hopefully. All right, so I'm just going to go through, there's two papers here. The first one is the second one, like this one. So let's see. 1008. Let me try this thing on. Can you guys hear online?
I can hear you.
Okay, that's good. All right, so anyway, there's two papers, both by this group, this William Koros group at Georgia Tech. So they seem to be like membrane central, for polymer gas separation membranes, which is it's a big topic in chemical engineering. So this is in the AICHE journal, right? So it's, we don't usually get that, but basically that's the, I guess it's the highest level for chemical engineering journal, specific. So usually it's a showcase journal. Oh, you guys might get that if you're members of AICHE, like you might get this in the mail, this journal, right? So anyway, so the reason I took this paper, because he's doing this ethylene ethane separation. So that's a big problem in the petrochemical industry. So you see like Dow Chemical, and then you'll see like all the Phillips Petroleum, and then the papers, the citations are from like Air Products, Dow Chemical, Phillips Petroleum. So like industrial research, right? So, and then DR Paul's another guy from Austin who's like, like University of Texas, Austin, who's doing this kind of stuff. So he's like an old school polymer kind of physics applied chemical engineering type person. So this kind of big name people in this field. I mean, that's the idea. So this problem of separating ethane from ethylene is a big problem, right? So anyway, in this paper, in all these papers, the Koros papers, they seem to spend a lot of the upfront end on the kind of the theoretical stuff, and then they pop in one simple kind of solution. And that's the way this paper is. So first he goes through and describes the problem. So first, so you have so we have permeability for the membrane is going to be it's going to have an absorption process of the whatever you're trying to separate. So here, basically, you're trying to absorb the ethane and then exclude the ethylene. Right, so the double bond one you want to exclude, and the ethane supposedly would go through faster. There's a smaller molecule. So one of SA would be like absorbing the ethane, and then DA is the transport of the ethane through the membrane, the diffusion coefficient. And then permeability is a combination of those two. Right. And then in addition to that, you have the selectivity, which would be like the permeability, so DASA for the ethane versus ethylene, the ratio of the two. So that's how well you're separating. So you want this number to be in the hundreds. That would be like what you need for a commercial membrane. So so the plots are going to be like this separation versus this permeability means how much is fluxing through. Then of that flux, how much is the thing you want, this A component. Right, so you're going to get, that's the plot you're going to have, is like selectivity versus permeability. And then the units are bar, which are some units specific to this. He describes the units here. Again, it's like kind of a lot of detail, but it's because it's for the chemical engineering, this ASHE journal, so it's partly, the articles are partly like a tutorial in a sense, I guess. It's kind of a weird journal. It's like a showcase journal, but a lot of the articles like Scientific American for chemical engineers, you know. Anyway, so in that plot, I should have brought some water. All right, so I mean, hopefully I'll survive. I think it's allergies or something. So reference 14 from that paper is this thing from 1991 by a guy named Robeson from Air Products. So anyway, they do gas separation, and he talks about that same membrane plot, like selectivity versus permeability. And then he kind of finds out in this paper that there's an upper limit to this. Like, in other words, as the permeability drops, the selectivity increases. And as you increase the amount you're pumping through the membrane, the selectivity drops, right? And he comes up with a kind of an empirical function to describe that. Let's see, he doesn't come up with a function to describe it, but he shows this upper bound, right? So he defines that upper bound. And it has something, there's a lot of things going on. One is that if you push more through it, so in order to get the material like ethane into the membrane, it has to dissolve in it, right? So you have to have a solubility. So the permeability is diffusivity times solubility. So it has to dissolve and it has to transport. So if it dissolves, it means it has to be compatible. If it's compatible, then it plasticizes the membrane. If it plasticizes the membrane, the free volume that you're trying to punch through can either compress or release, like it can change the transport. So that the fact that you're driving the thing through means that you're kind of putting a solvent into it. And that changes the transport properties. So that can drop your selectivity, because if you have looser pores that you're pushing through, then it's not as selective. The rigidity of the pores is what's selecting. They aren't pores like molecular holes, like free volume in the material, right? So anyway, that's kind of the idea of this, more or less. So in this Robeson thing, he so you don't really need to read these papers, but I guess you can glance at them. But he mentions that I think in this paper he mentions, yeah, this equation. So this is the parent equation for the concentration of the material that goes in, right? And this is made up of two parts. So it's got a Langmuir part, this term, and it's got a Henry's law part, this term. So if you have, so Henry's law is alternative to Raoult's law for low concentrations of things. Okay, and Raoult's law is an ideal gas law. It's an ideal law for ideal gas mixing. It means that if you have a mixture of gases, the fraction of the gas that's one component, like oxygen and oxygen nitrogen, that fraction times the total pressure will give you the partial pressure of oxygen. So it's a linear mixing rule. If you put in half oxygen, half nitrogen, then the partial pressure of oxygen is half of an atmospheric pressure. Right? Or if it's 20% oxygen, it's the partial pressure is 20%, like 0.2 bar would be the pressure, partial pressure of oxygen by Raoult's law. So that's an ideal mixing law. In fact, when things mix, they can kind of interact, so you don't get ideal mixing, right? And that's especially true when you get to dilute conditions, where you're just putting in parts per million of some kind of polyaromatic hydrocarbon, and it's going into water. So the concentration of the polyaromatic hydrocarbon can be quite different than that linear Raoult's law rule. You just have a small amount of gasoline or something that's dumped into the ocean. Right? So the water concentration, so environmental, I use Henry's law because it's always like a small fraction. And in the case of membranes, it's also a small fraction. So that, in fact, this K would be would be 1 over the saturated pressure of the material, like its equilibrium saturation pressure. Raoult's law would be like the saturation pressure, and then 1 over that is this K, Henry's law constant, and it doesn't equal 1 over the saturation pressure, but that would be the metric that you'd measure it by. Like, does it dissolve better or worse? You compare K to 1 over the saturated pressure. Anyway, so that's Raoult's law. That's kind of simple. Then this other one is a Langmuir equation shifted around a little bit. So the Langmuir equation is if you have a surface and then you have sites of absorption on the surface, and then those sites can fill up. So there's a limited amount that you can push through into the surface. And then in this case, it's assuming that that's going to go into the solution. So the Langmuir, there's a pretty good wiki page for Langmuir equation. I mean, it gives basically everything. It's better than the books, I think. So basically this equation, so the surface fraction that absorbs, it's going to equal the pressure, the partial pressure, and then this equilibrium constant between free and absorbed species, and then a number of sites on the surface, like the surface area. So that's the equilibrium constant. You can see that he's kind of got that a little bit different. Like he's got this B term. So he's got, instead of 1 equilibrium constant and the pressure, he's got this B term and the C term and the B terms. So this would normally be like Ka and Ka, but he's got kind of changed a little bit here. But it's basically the same as the Langmuir, calls it hole fitting, solubility, whatever. So the two things have different, this is a linear law. So the higher the pressure, it would go straight up. This is a law that it'll plateau out. Like when you get to high pressure, this just becomes 1, right? And then you just have CH, because the top term, bottom term are the same at high P. Right, so this thing plateaus out. This just keeps on cooking when you get to high pressure. And at low pressure, this guy's linear because this thing becomes 1 in the denominator. And this thing is just the same as kind of Henry's law, right? So it's linear at low pressure and it plateaus out at high pressure. And then this thing's just linear all the way through. So it's got those two processes that go into a C. So anyway, there's several dual processy things in here. That's one of them. Like they talk about dual mode sorption theory. So that's what they're talking about in that when they mention that. Anyway, so that there's that thing, and then this is the 1990 paper where he comes up with these equations for the lambda. That's the separation efficiency, blah, blah, blah. Then he comes up with the things for these kind of complicated activity. It's basically using an Irene rate theory or Arrhenius function to describe the sorption and the maybe it's not in this guy, maybe it's in this. So I think it's the second reference here. 16, 15, I think it's 15. This one, let's see, do I already have that open? Groups and yeah, so this is the one that has the lambda. So these are the sizes of the kind of the molecular diameters from, he says it's from the 612 potential, but I don't see exactly where he gets these diameters from. the kinetic diameters of the fast and slow. So somewhere it gets the diameter of the gases. You could get it from a group contribution method if you wanted, just like look up in a table and put the thing together. And then you can get this lambda number. That's not how he gets it. Then you get, this is basically an Arrhenius type function, like the diffusion coefficient goes exponential of the energy over KT, right? And then there's some entropic part to it, I guess. So these are just, so you can see that the constants start to pile up here. So it gets to be indecipherable. The more constants you put in, then it will become like empirical at some point. But some of these constants he can pull out of his hat somewhere, like the sizes of the molecules. And then these B and F, the F number, he has no idea what it is, but the A and B you can calculate. So you don't really need to understand this, but just the background for the equations are there. Oops. So, oh, this is our paper. So this stuff all comes from one of these references, like 14 to 16. This is 14, that's 16. Let's see. And 15, that's 15. So I haven't opened 16. They're all in here. Getting 16 upper bound. This is the same as the first guy, but it's 1999. And this is where he gets, this is where the alpha, all these, this is where the lambdas and things are. He explains it better in this paper. This is the original paper where he comes up with this F number and how he kind of guesstimates the F number. And it's not that important, but basically you can kind of see how you go from science to empirical applied, you know, if you want to look at it. You don't necessarily have to look at it that closely, but anyway, so and this actually the only point of this whole section, right? I mean, other than to just demonstrate his power is and understanding this, is to say like, so that there's a variety of ways you can predict this upper limit. So you want this number to be large and you want this number to be large. So you want to be like over here, right? You want to have a separation of like 200 or 300 to make it commercially viable. And then you want to have a flux of like maybe 100. So you want something like here, and all the membranes, the best membranes they can make with a single polymer are down here. And this is the theoretical, quote unquote, theoretical absolute limit that you could get to. And the flux you're looking at is 10. So the most separation you get is like 6, which isn't good enough. Not anywhere near good enough. That's just like, you can get that from just taking the stuff and putting it in water. I think if you put it into a solvent and then one has a different vapor pressure, you can separate that way too. You can get a separation efficient about 3 by doing that. So 6 is just like putting it into a solvent and just letting it separate that way. So it would heat up the solvent and separate the gases. So that would be a kind of an easier way to get to 3 than making these membranes. So in the cryo, like, so right now they're doing cryo distillation, which has this huge energy penalty, which he mentions at the beginning. Someone told me that this process takes like 1 or 2% of all the energy that's used in the world. I mean, that's what someone told me, but then I went and calculated, because he gives let's see. Yeah, in this paper, he tells the number, right? He says what the energy is, 10 to the 12 BTU. So I looked up, like, what is the total energy on Earth that's consumed? And it's like 10 to the 15. So this is 1/1000th or something of, anyway, it's a sizable chunk of the total energy. It's a lot of energy that's used to do this in the cryo distillation process. And basically you get rid of all that energy if you just do this separation. That's the weird thing about the petrochemical industry and the CO2, you know, because for every gallon of gas that you have, it's like 5 gallons of gas have been burned to make that gas from the oil that it came from. So that, like, in other words, you could cut our CO2 production by a factor of 5 if you got the efficiency of the processes to be something reasonable, right? So it's kind of like there's a lot of room to play, even just if we stuck with gas cars, that would be enough, you know, if you could just correct the efficiencies and processes like this, right? So basically there's a lot of room for efficiency and there's money to be made by doing that, right? So anyway, so for whatever that's worth. I mean, you could also just get rid of the petrochemical industry. That's the other option. But basically, there's room to play here. There's plenty of room to play, and there's money to be made doing it, right? So anyway, so is that the upper limit thing tells you that this isn't going to work, and that's kind of the point of this. Like the first question is something like, why isn't it going to work? The reasoning behind the limit. So where is that? So you actually gonna have to kind of glance at that stuff. I'm not sure you can answer that because the reasoning in the end is just it's an observation. Like they observe it first, and they came up with some equations and kind of predict it. And they're based somewhat on these absorption models and the transport and the issue of plasticization of the matrix of the polymer. So there's a lot of things going into those equations if you look at them. And then the size difference of the molecules. And there are membrane separations like CO2 that are in the other paper that get 100 or maybe 500 separation and at a permeability of 10, bearer or whatever it is. So I mean, those are commercially viable. Like they're really viable, and they want to use those for separating CO2 from flue gas for coal plants. But coal plants aren't economically viable anymore. So that whole thing is kind of crazy because natural gas is like half the cost of coal. It's like coal's dead anyway. Yeah.
Will flue gas be SO2?
This SO2 they can get out. They make gypsum with it.
Oh.
Did you go on the tour of the? You didn't go on that tour. We toured the Fort Miami plant. All the gypsum in your wall boards is the SO2 and the flue gas. Yeah, no, it comes from the flue gas. They burn the coal, then they put in some.
Yeah.
What is it? Yeah, limestone, but you can get it from flue gas too. And most of it's come from flue gas now because it's cheaper. So they just precipitate out the SO2 into whatever's in wallboard. And then they barges in the Ohio River take it someplace and they press it into wallboard. So like your house or your apartment or whatever has the exhaust gas from the coal plant in it for the walls, it's pretty weird. So who knows what else is in that, but basically it must be okay because if it isn't, we're all dead anyway. So maybe it doesn't make any difference at some point. But yeah, so the SO2 is not a problem anymore. I mean, if they've already put, because the EPA made them put these scrubbers on it, so there's nothing coming out anymore, I think, as far as I know. So the CO2 is the big thing. I mean, the carbon, because if you burn with, if it's got more hydrogens on it, then you end up with water as a product. If it's got more carbon, you end up with CO2 as a product of combustion, So basically coal is pure carbon. So that's the worst you can get. That's the theory. In fact, there's also some other issues like the temperature, like there's a thermal efficiency for the thing. So and the coal plants are burning at like 4,000 degrees or 3,000 or something. So it's a huge temperature compared to the river water. Right, so the temperature difference governs the efficiency. So basically, the efficiency of that thing is like 70%, and the efficiency of burning gasoline, which has a lot more hydrogens in it, is like 20%. It's like if you figure that into it, coal starts to look better if you look at it the right way. It's not good, but basically, if you look at it the right way, there's some argument to be made that you could scrub out the CO2 and this could be viable with membranes, if you could do something with the CO2 once you make it, other than pumping it into like mines under Illinois. Like the pilot thing is outside Chicago, and they have limestone pits or something where they pump the CO2 into it. Anyway, there's no commercially viable where they've ever done that, So, but there are people looking at polymerizing CO2, things like that. So who knows? Unlikely that coal will be existing in 10 years, really. Like it's just not, it isn't viable. They aren't building new coal plants, and the others, like Miami, so Zimmer shut down, the largest coal plant, I think, east of the Mississippi or something, right? And that completely shut down because it wasn't economically viable. The Miami Fort, which also supplies Cincinnati, and also is pretty large, that's going to be done in like 5 years. they're going through like shutdown. And then there's one coal plant that the Ohio state government in the Illinois in the Indiana Ohio border, somewhere in the middle, that they funded to keep going. They were going to shut it down, but they kind of gave them money to keep it going, you know. So it's like kind of they're at the end of the lifetime, I think. But anyway, the Department of Energy is still dumping money into like separation membranes for CO2. That's still a pretty hot topic. So you can get unlimited research money for that if you want to do it, you know. So it's kind of like, it's almost as if they're still thinking in the old days, you know, like they haven't, but they have parts of DOE are thinking way in the future, parts are now, and parts are like kind of stuck in the past, you know. So that's the way it goes. Anyway, so he basically says that this isn't going to work. I mean, he shows plots and basically says and explains why it's not going to work. It's because of this limiting factor in the thing. So this is showing like kind of this isn't so then he gives some other options, like what are the other options in the membrane arena, right? So advanced membranes for ethane ethylene separations. So there's a few options, right? And he kind of goes through them and knocks them all down. So the first one is you can have a porous membrane like a polypropylene where it has pores in it, and then you can put a liquid into the pores, right? And then inside that liquid, you can put like a metal ion that will bond with a pi bond and ethylene. And then it selectively absorbs ethylene. It can transport across the pore that's got liquid in it, right? So that's one option, right? So there's some papers on that in here. Coupling separation and a review on facilitated transport, and then chemical complexation. So I don't remember which one of these is the best one. There's two that he cites, like the review is probably the best one. So actually the first paper shows the salient point. You can have silver, it can bond with ethylene, the pi bonds and ethylene, and then it can transport across the membrane. Some of these show, so you can have pores filled with a liquid. So these don't have to be nanopores. These are micron scale. So these can be any of the processes of making porous membranes from like last week, like the amide polymerization thing can be, or it can just be stretch polypropylene and get the crystalline holes show up, or whatever, put starch in and flush it out, because the capillary force keeps the liquid in. And if you have a polymer that doesn't have transport of gases, then it just magically goes through these pores and zips through. The problem is it evaporates, and you can contaminate. You're using silver; it's kind of expensive, and then it can be poisoned by other gases. It's a petrochemical stream. It's got all kinds of stuff in it, sulfur for one thing, but a lot of other things. So those things can bind and poison the membrane. So there's a problem with the turnover of these things. They can get the flux through it. They can get like separation of hundreds, selectivity of hundreds in this thing, but basically it hasn't been commercialized because it's expensive to put silver into membranes you're going to throw away after. It can't be recycled, you know. And then it's like the idea of making printed electronics. We're going to do this in Africa, make printed electronics. Turns out the ink is silver, you know, and we're going to put them for moisture sensors, put them out in the fields. Well, when people hear that you have silver, you know, silver things out in the field, they just go and like take them, you know, cash it in. So maybe it's the same thing with a membrane, like, oh, it's all silver. What are you doing with it? I mean, so anyway, yes, this problem with using milbo metals, the cost of it. One of these shows actually like chemical complexation. These papers show like the industrial process, like, so it's kind of, this is easier to look at. It's easier on your eyes. You can figure out what's going on, you know. They have the membrane separation. They show kind of how it works, the pores and how it zips through the polymer and goes into the selective liquid thing. You can use also like ionic fluids, and this is a bunch of research going into like what you can put into liquid droplets to transport. So that's one option. That's option one of this thing. And there's a few papers on that in here. Then option two in this paper, let's see. Option two is molecular sieve. Oh, there's also facility. You can have, instead of having things that can evaporate, you can put dry, transport, solid facilitator transport. So you can put silver in, like a silver organic complex or something, and then it's not in a liquid. It's a dry state. So PEO, polyethylene oxide, the thing we had, like it's kind of like water soluble. It's used to make hand gel and stuff, right? So, and then you can, on the oxygens, you can associate the silver ions to the oxygens on that, and then just mix that in with the plastic. And then that will be a facilitated transport without any liquid. It won't dry out. It still has a problem with poisoning from the process streams, right? So that's a step forward. And then not sure if they show an efficiency, a separation efficiency on this thing. I mean, they're kind of, yeah, here. So they're showing like, I don't know, some big numbers here, right? The low with just the polymer, and then like when they load it up, they get high, like in the thousands. So, I mean, it's actually like, if it didn't poison, it would be like commercially viable, or if you could like rejuvenate it or something, right? So, but you can't, like they poison it, it's dead and you throw it away. And then you have to go in manually, like change the filters and things. So change the membranes. So that's not great. Then the other thing he mentions here, so he's going through like the entire workshop of what they could do to solve this problem, right? And then they say like molecular sieve. So you just throw in zeolite. So zeolite is, I didn't put any links to what zeolite. In the thermo class, I talk about all this stuff, but basically there's a whole field of these metal organic framework molecules that they're crystalline, but they're nanocrystalline. So they have pores in them that are of controlled size, and you can do a lot of stuff with it. It's a whole field. I should put some links to what MOFs are. And then zeolite's something older, which is where you use a surfactant template and you put a sol gel in and you make a ceramic particles that have nanoscale pores in them. And you can also use a block copolymer as a template and then somehow make the ceramic phase of the water soluble part of the block copolymer and then burn it and then make these zeolites. Or there's actually also natural zeolites. So you get minerals that you can pick up that have pores in them. Anyway, so there are these things that have pores that are the right size to select something of the size of ethane and ethylene. So you can just dump a load of that into your plastic, and then when it zips through the polymer and it reaches these ceramic particles, only one of them is going to get through. So the higher the loading, then you can get the separation, and they don't poison. Like the sulfur, all that stuff won't hurt it. Problem is, they don't have any selectivity because they're just round holes, right? I mean, so he's building up his argument to use this carbon thing where he has not round holes, he has sheet holes. And then you can do topological selection of the things. So the zeolite thing is really a feed, and there might be zeolites with square hole or rectangular holes. I mean, he didn't look at that, but basically he says that doesn't work because the selectivity. Let's see, so these are for all these molecular sieves. You can see it's below 10. So he's looking for 1,000, like 2,000, or maybe 100 would be good, or 200. But basically, below 10 isn't going to cut it. You know? And basically, he's looking for a permeability at 10 and then a flux of in the 1,000. So he wants to be like up here, and he's down here with these materials. So the guy's made all this stuff, right? So he had a pretty active lab going on. That didn't work though. And then he finally just does this thing, this carbon, I think this paper is linked to that too. This kind of carbon process, the facilitated chemicals, solid facilitated reference 5 pyrolysis. Yeah, so this is the same guy, Georgia Tech. And then this is where this is in membrane something or other. Carbon, so that's a pretty good journal. But it's basically like the process. This is just how you burn it. And then you end up with big pores and little pores. Little pores are between these graphitic layers. And then the ethylene can fit through an ethane. The ethane can fit through an ethylene. Ethane is linear, and somehow the ethylene won't fit through this. So you can get a separation because topologically they're different. And I think he doesn't actually show any numbers here. The problem is that he says this is the solution, but he never gets above 10 in the selectivity of this thing. And so he shows like this is the original before burning it of these aromatic polyamide film. So it's like a nitrogen ring thing coupled to an aromatic ring, right, in the backbone. Anyway, so before you burn it, it's below 10, that's no good. And then after he burns it, he goes through this burning process at different temperatures with and without oxygen. So this is typical for making like carbon fibers for epoxies and things. This kind of pyrolysis technology or empiricism, like it's basically witch doctor, but they tried everything. So with oxygen, without oxygen, different temperatures, different times. So making carbon fibers for like aerospace is a huge industry. Like if you talk to people at Wright-Patterson, they have a whole group of like 20 people just working on making carbon fibers from polyacrylonitrile. You just cook it, and it's all just cook it in these ovens for different lengths of time. Actually, every major lab has groups working on taking polyacrylonitrile and making high strength fibers from it for composites, right? Anyway, so that technology is pretty much like well developed since they started using carbon fibers for strong, composites, basically epoxy composites. So anyway, he's just applying that to this field. Like you can just go, there's a rich literature on that. You can just stick it in here. He's got a different goal. He's not interested in strength, but he's kind of interested in this separation. He's measuring separation as a function of these oven routines, that if you look in the carbon fiber business, you'll see plots like this all over the place where they're looking at cooking it different ways. I mean, the polymers he's cooking are a little bit different, but they do use these polyamides for that also, besides polyacrylonitrile. If you want to have a good leaving group, like nitrogen is a good leaving group. So if you have nitrogen in it, that's going to come off fast when you burn it, and the thing will collapse down to carbon. Anyway, so this kind of is more like, this is the problem. So this is kind of good to look at. This isn't in the homework, but basically, like you can imagine what's going to happen when you burn a film, right? It's going to like crumple up. Like you've probably experienced this when you overcook something or whatever. Or it's going to have wrinkles, or it's going to fold into shape because you need to have it flat. So this is probably the most important picture of the whole thing. It's like it can work, sometimes, but maybe not all the time. There's a lot of twists and turns to trying to go through these routines, things that you don't have when you have a 1D fiber that you make. I mean, the fiber will shrink, but basically you're still going to have a fiber after you cook the polyacrylonitrile, and that can be used in a composite to make an airplane or something. So, but basically this thing, it's 2D, so it can have a lot of things that can happen to it, not just shrink. It can crumple, wrinkle, fold over, bend, right? So basically anything can happen and turns it from 2D to 3D. It's not going to be good for this. Anyway, so it's that business. Anyway, in the end, he says this is the answer, but in the end, like, he doesn't show much improvement. Like he gets to 15 instead of like 6. And the target again is like 200 or 300. Yeah, at 10, right? So he hasn't really done it here. And he's put this into cylindrical, instead of sheets, he puts it into fibrous separators, and he kind of has some mapping out of how that works. So anyway, that's the point. His conclusion is like there is a way to do it. It's by burning the things. That's kind of interesting. So that's one paper. Any questions on that thing? I mean, I think it's kind of interesting. I mean, in terms of membranes, this is as good as it gets. We're kind of driven to membranes this year, but one of the undergrads is working on that for Dow. But so anyway, it's not a bad thing to look at. it's good to do something kind of topical to see. So this is the other paper. This is the paper that's this year. That other one was from the 90s or something, right? I don't remember when. This thing is 2013. Okay, so this is, I mean, relatively old for our taste, but this one's just this year, just came out, or last year, I guess, 2022. And it's in macromolecules, was kind of a review. And the point of the review is to say, so it's a little bit nuanced in that you have to know that this plot exists, but he's basically saying that this plot is worthless. That in fact, the main things that are going on when you industrially make these fiber membranes is the plasticization problem, something called anti-plasticization, the dual mode transport thing, and then non-uniform whatever, that's processing. In other words, when you make these fibers, it's not going to be as if you have a model thing that's been annealed. It's got all this residual stress left from the extrusion and all the processing steps of, because it's got to be non-equilibrium to get the pores to begin with. So in that sense, you're going to have, in terms of the free volume, it's not going to be a single free volume across. It's going to have all these regions of different things, and then whatever else, asymmetry, whatever. So basically that stuff has to be looked at, and then so those four things are going to be like the dominant features. And he has some cartoons about how that works. Like you push I think the main point of the plasticization is you push the gas in. The gas has to be soluble for it to go into a solid polymer. If it's soluble, it's plasticizing it. So when you go to the high permeability, in other words, high transport of the thing, the selectivity has to drop because it's plasticizing the thing as it goes in. And then that means the pores are going to just release, right? Then the other things, so the dual mode, this starts to look like last week's paper, like there's domains, and there's a paper for each of these things in here. So let me just go through those. So the first one, the facilitated transport, can call it solid facilitated, then pyrolysis. Where are these things? Pyrolysis, binder, these are things, equations. See, it might be somewhere else. Koros. Well, dual mode transport is here. In upper bound. That's the pyrolysis thing. These are just the equations. Maybe I didn't put those things in here. Here, one of them is this dual mode transport. That's one of his issues. This is the reference he gives for that, which is from like in the 80s, I think. But it's kind of pretty involved. This guy, he starts out talking about the two. No, it's Henry's law. The top one should be Henry's law. Like, in other words, the concentration in the gas is the pressure. So the pressure times the constant gives you the concentration in the film. So if the K is Henry's law constant, then that's Henry's law, right? So then this thing is supposed to be the Langmuir absorption equation, but it's written kind of a little bit different format. But you can see there's like a 1 minus something and then something on the top. So kind of somehow you can get that Langmuir equation from this equation. So it's got these two kind of equilibria constants that have to do with how things are absorbing into the thing, but this isn't about absorption. So that's the weird thing. This thing's about gas transport, right? So it's not about the absorption of the things, but he starts out by talking about absorption. If you read this, that's kind of like the easiest part to look at here, because the rest of it, he talks about the difference between concentration and activity. So you have the activity coefficient. So that's the solubility term. That's having to do with like the interaction parameter of the polymer and the gas. And then I haven't actually figured out the dual mode transport thing. he's talking about the two absorption models, which are those are equilibrium models. So they're not kinetics like transport. But he fits that into this flux equation. So I guess it's the solubility times the diffusion gives you the flux. So that's kind of true. I guess that's the point, that he's got two modes of just the two things, the two absorption mechanisms govern the two fluxes. So I'm not sure how that dominates. In other words, he's saying in this paper that dominates the process, right? So he's saying that somehow interferes with this plot. Anyway, that's his dual mode thing, dual mode transport involving saturation of unrelaxed free volume. So that reference 7 doesn't mention unrelaxed free volume. So it's kind of a weird, anyway, however you want to interpret that. The question in this is like, he gives these 4 things, what are they? You know, so I think that you can spend some time figuring that out. I'm not sure I've actually done it yet, but basically that's my interpretation so far of the dual mode. The plasticization is what I said. Anti-plasticization is that he shows that in this picture, like you can restrict the transport. Somehow the polymer, the solvent going into the polymer can restrict the transport. That's kind of the anti-plasticization. I have this reference 6 somewhere, but I didn't. I'm not sure how I didn't post it. I thought I had posted that, but we can get it here. Effective anti-plasticization. Sometimes you click it and it goes there. So I guess I'm having a hard time. It's thinking, it's good. This is just the process that we used. Macro, that's this paper. There. You get a PDF, yeah. I think it wants to. Oh yeah. That's a good sign. I thought I posted this, but I guess, yeah, this is Dr. Paul, the guy from Texas. So he's like, he might be, I don't know if he's dead, or I shouldn't say that, but this is 87, right? So Dr. Paul for a long time was Mr. Polymer, kind of, but kind of a businessman. Like he always wore a 3-piece suit. It's like he was a little formal, you know, especially coming from Texas. So you wonder, but basically, I think he was in industry before he went to Texas, and he developed like a whole, especially applied polymers, like polymer mixing. He wrote a book on polymer mixing, and then he's involved in this membrane stuff. So everything has a link to like industry, you know. So it's a big. I mean, he had like 50 grad students, some huge number, you know, like, and then postdocs and whatever. He basically was an industry to himself. I'm not sure if he's still alive. Maybe we could find out. Not Children's, no. What's this stuff? So is he still alive? What? Yeah, see, PhD 65, right? It's a long time ago. Emeritus, so he's retired and apparently still alive. So if he has PhD and he was 30, how old would he be? 65, he'd be old, right? That's 50 years ago. So he'd be in his late 80s, that's what I think. So yeah, he's still alive. People look at Joe Biden. So anyway, so how old is Joe Biden's 80, I think he's going to be like 80. If he goes another term, he'll be like 86 or something. So like the guy in Nigeria is pretty old too, right? Is he in his 80s? Yeah. Yeah, so they say that the worse I was reading a thing about like people, like your brain deterioration as you grow old, and apparently like all the people who are in like death camps in Germany, those are most of the people that are like super smart when they're 90 years old, or be able to cognate when they're 90. So basically, if you're tortured when you're young, like bad things happen to you, like later on, you get a benefit from that somehow. They didn't say why. This was an observation, I guess. So anyway, maybe DR Paul's or Biden or someone's in that category. But right. So anyway, this has to do with the anti-plasticization thing, which I don't think I've exactly figured out what it is. I think it's got something to do with the miscibility of the things, I remember now. Sorry, I remember. This has to do with the free volume thing. So if you have, I'd say like you have Raoult's law, you have ideal mixing, right? So there's no volume change on mixing. So you have the partial pressure equals a concentration times the total pressure. That's ideal. But if you, in real systems, like if you mix alcohol and water, you get a lower volume than the two mix, significantly lower, right? So like 10% lower or something. So anyway, you can have positive and negative deviations from the, so this is a plot of the kind of the free volume or the volume, the dense one over the density versus concentration. So if you pump in a thing that's got that kind of behavior, then the free volume is where you're transporting your stuff through. If the free volume drops, the stuff can't get through anymore. So your permeability will drop. So you have plasticization. So the two things are really odd. The one, they're both arguing to the same point, the permeability will drop, but they're doing it from two different approaches. One is saying that you have this non-ideal mixing that leads to lowering the volume. The other one says that when you loosey-goosey the thing, the pores collapse. So loosey-goosey generally means more free volume. It's like they're arguing that more free volume or less free volume both lead to lower permeability. Basically, you don't want to have anything happen to the system, right? When you so anyway, so that's the anti-plasticization thing. This is nice because it brings in thermo, and it's kind of a well-known thing. It's mixing things, and he doesn't mention, I guess, that you can get the opposite effect. You can get an increase, but so there's positive and negative deviations from Raoult's law. It's in the chemical engineering and thermal book. I want to look at it, but anyway, so this is actually like a chemical engineer's answer to the problem, right? Because it's a main course in chemical engineering, and then like he's just directly applying it to membranes and plastics, and then has this. So this is directly a product of the chemical engineering education that this guy had, or taught or whatever. So anyway, so that's that one. That's the 5. I'm not sure if I did the 5 things here. This is the paper, the 5 things. So we solved the dual mode, we solved plasticization, we solved anti-plasticization, we solved. And this one, like this reference is this thing is a dissertation from Texas, I think, University of Texas, Austin. So I wasn't able to get that. I might be able to find that, but basically he must go through, I imagine he goes through like, and I think it's probably with DR Paul's thing, right? So this guy looks a lot like DR Paul, doesn't he? I think they're like really the same person. Not transformed. Let me see, hold on a second. Let me just make sure that, right. Oh, that's because there's a picture of Koros here. Maybe Koros was Paul's student or something like that. That's why I thought this was a picture of DR Paul, and it's like the same guy, But wait, yeah, he looks different. Sorry, that guy and that guy are 2 different people. That's good, comforting. Anyway, so basically, if you can find that, it might help to kind of look at it and see what they did for the PhD. But basically, I couldn't get it. This is just a dual mode thing. That's not it. But so that's about it for this thing, for that homework. It's basically like look at those 2 papers and fish through and see what sense you can make of it. And I put some citations in there you can kind of look at. I mean, next week do the machine learning and artificial intelligence stuff. Having how it's being used in research, like what people are talking about doing. That's a big, I mean, it's a big topic, and most of the meetings will be like the sessions on this stuff, so. And kind of go through that a little bit. So that's about it. Any questions, anything? So let me quit early today. Got a bunch of people online. I guess 1, 2, 3, 4, 5, 8. So we got about half the people. That's good. All right. Let's shut this guy down.